Hi everyone and welcome back to Physics 2B. This week we'll be discussing magnetism, and I have a couple of images here to kind of get your mind rolling on the idea of magnetism. So we're first going to talk about magnets, but I wanted to quickly talk about kind of why it's important as a whole planet. So we don't only see magnets in our day-to-day lives, like putting a magnet on the refrigerator, so we have magnetism going on there. We also see it planet-wide. So this is a depiction of Earth, and the Earth acts as a bar magnet overall. So this bar magnet has a north and south pole, which we'll talk about in a minute here, and it creates a magnetic um, field around it. So that's what these loops are. Okay, so we have something that's kind of covering our entire planet. It's a global thing here, and it's important for us because we have something so close to us that could potentially damage our planet. Um, and if we didn't have the magnetic field there, we would not be here, most likely, or it would be a much harsher environment for us to live. So this is a depiction of what I am talking about. So the star that's closest to us is, of course, the sun, and it has solar wind that gets ejected, thrown around, very chaotic, and it comes to Earth, right? So we see sunlight, we have sun rays, and this wind is much more intense than we feel it just going outside on a hot summer day, right? But thankfully, our magnetic field shields us from that. So you can see here we have these loops of magnetism, these magnetic field lines, and you can see that it's like shielding us from all of that harsh solar wind, and it kind of gets trapped on these um, magnetic field lines from Earth. Okay, so this stuff is not just important for day-to-day life, it's important for our entire world to survive. All right, so let's talk about magnets first. So again, like we've said, we've played with magnets, most likely, or you know how it kind of works maybe. It seems kind of like a magical thing, right? You have some sort of um, magnet that you want to put on your fridge and it just sticks, right? Well, that's because it has a few universal characteristics. So the main two that are really important is that like poles repel and unlike poles attract. And notice the similarity between the um, magnets here and then charges that we've seen in the past. So remember that charges, we had like charges repel and unlike charges attract. So this is very similar to that. But now we're looking at poles of magnets. Okay. Another important thing to note is that they are impossible to separate their north and south poles. And if we try to do that, if we cut a magnet in half, we'll still get north and south poles. If we try to do it again, we'll still have north and south poles. And that goes all the way down to the molecular level. We cannot separate these poles to where we'd have like a monopole. We can't do that. We'll always have a dipole, so that we have two poles, dipole, okay? We also have a couple of terms. I keep saying north and south pole. Well, the north magnetic pole is going to be the north-seeking pole. Whoops. Whoops. There we go. The north-seeking pole. And we have the south magnetic pole, which would be the south-seeking pole. And, oh, whoops. This comes from the idea of Earth. So Earth, I said before, is like a giant bar magnet. So pretend that we have a bar magnet inside. And we have a external magnet, and we're trying to find what pole this side is, this right-hand side, okay? So we have it on Earth, and the north will point towards our north geographic pole, okay? So our north geographic pole or our south magnetic pole, okay? So we call this our north magnetic pole here on the bar magnet. And so it is north seeking, okay? Then we have our south magnetic pole here, and it is south seeking, okay? Um, okay, so let's go ahead and move on here. Okay, to ferromagnets. So ferromagnets are materials that exhibit strong magnetic effects, and these are a lot of times metals, but not all metals are magnetic. Um, but this is going to include iron, cobalt, nickel, gadolinium, and these can respond very strongly to magnets and can be magnetized themselves. So we can take a piece of iron and actually magnetize it, so then it's a permanent magnet now. So it's like inducing the magnetism, kind of like how we were inducing a charge before, we can induce magnetism. And so this is a depiction of that. So we've got um, a iron bar here in between two magnets. So we have a north and a south pole around it. And through heat and tapping, so kind of agitating those elements in there, or ions, we can now get a north and south pole here. And these will, let's see, these will now be magnetized. So this is the ferromagnet that has been magnetized, okay? Um, one other thing to note is this temperature at which we can't magnetize whatever the material is. So this is called the Curie temperature. And so this temperature, again, you can't magnetize above that temperature. So an example would be for iron is 770 degrees Celsius. So above that temperature, we can no longer magnetize that metal. Okay, so there is another way to induce magnetism or have magnetism, and that is through electrical currents. And we call this an electromagnet once we have that material. And the electromagnetism is the use of electric current to make magnets. So we have a couple of images here. This is going to be your electromagnet. Okay, this system here, and this is your bar magnet. So this is your bar magnet, and this is your electromagnet. Okay, so notice the similarities here. So these little pieces of things are called iron filings, and they're typically used to show the magnetic field of whatever you're looking at. So in this case, you can see these iron filings are going kind of like in lines, right, from the north and the south poles. And you can see that same effect here, some sort of north and south pole interaction there. So this is loops of wire here, where you see the um, silver here. These are loops of wire, and there is some current going through those loops. So we can say that it's going like that direction through the loops, okay? Kind of like a spiral. right? And with that comes a magnetic field. So the magnetic field goes straight through there, and then you have this like north and south pole looking magnetic field, right? You have something happening on either side here. Okay, so let me erase that bit. And here is just another example here. This is a, what are they called? Oh shoot, I forgot what they're called. Not a CD, it's before CDs. Why can't I remember the name? Oh my gosh, how terrible is that? Well, I never used them, but it was a little before my time. But it's just another way that we have some induced magnetism due to current, and we'll talk about some other examples here in a bit. So, like I said, we can induce magnetism through current, and current is the source of all magnetism. So, an electromagnet creates magnetism with an electric current, like I said, and a current loop produces a magnetic dipole. Like we said, we always have a dipole, we can't have a monopole. Magnetic field that acts like a north and south pole pair. So, this is just another depiction. We have some sort of magnet here, north and south poles. We have a electric field, or I'm sorry, current by this electron. Sorry, we have an electron going around this magnet. Okay, and so we have induced a magnetic field here. Okay, and so these are the same idea here. Okay, so these are showing we have some sort of current happening and in turn have a magnetic field. So I keep saying the term magnetic field. What does that mean? So a magnetic field represents the magnetic forces which act at some distance, and this is very similar to an electric field. Okay, so with an electric field, we had electric forces that were represented by these lines, but now we have these magnetic lines, magnetic field lines that are representing the magnetic field. So we sometimes call the magnetic field B field because B is representing the magnetic part, and kind of like how we were saying E field, or maybe I said it a couple of times for electric field. So magnetic field lines represent the strength and direction of the magnetic field. The direction is defined to be the direction in which the north end of the compass needle points. So if we have, it's the north end of the compass needle point. So we have the direction here, there, there. In this image, we have these little needles, like a compass needle, something that you would use if you were, I don't know, hiking or something, and you might have an app for that now. But there are actual compasses that the needle will point towards geographic north, or yeah, it would be geographic north. So this is going to point towards the north-seeking pole, which is going to be the South Pole. So, whoops. Okay, so we continue all the way to here, and this represents the magnetic field line. All of these. So if you connect all of these, we have these magnetic field lines, and we can figure out what is going on inside of the magnet. Well, the magnetic field just keeps on going through that. Okay, so these are all the same thing, all the same depiction, okay, of a bar magnet or some subtype of magnet. that has a magnetic field, and so magnetic field lines to represent that. I just want to quickly mention these guys. This is when we have a current involved. So we have a um, current that's going around in a circle here to the right. And with that, we'll have some sort of magnetic field going around that loop of current. Okay, and we'll talk a bit more about the direction and so forth in a little while. But just to kind of introduce the idea that we can relate the two, the current and the magnetic field and their directions. Okay. So same thing with this guy, we have a current along a wire, a current carrying wire, and we have a magnetic field that's going around that then. And again, we'll talk a bit about that in a bit. And we can use something that's called the right-hand rule, which I'll talk about later, how that all works. Okay. All right. One last thing I want to talk about is the properties of a magnetic field. So the first one is that the direction is tangent to the field line at any point in space. The strength is proportional to the closeness of the lines. We saw that with our electric field lines as well. It's proportional to the number of lines per unit area, um, perpendicular to the lines, areal density, but basically just the closeness of the lines. Okay, magnetic field lines can never cross, so the field is unique at any point. This is the same thing as equipotential lines. Okay, so equipotential lines showed that same thing. Magnetic field lines are continuous. So they form closed loops and they don't have a beginning or an end, and they go from North Pole to South Pole. So similar to electric field lines, they went from positive to negative. We have North Pole to South Pole. Okay. All right, so I'm going to go ahead and pause here and continue with our discussion on magnetism with magnetic force.